All right, in Unit 1, we're going to be talking a lot about motion, and most of that motion is going to be geared towards the one-dimensional motion. And when I say one-dimensional, that just means we're looking at objects that are moving, maybe it's left and right, and that's the one dimension that we're focusing on. Or the object could be moving forward and backward. That's the one dimension that we're talking about. So we're keeping it super simple in this first unit by just keeping it in one dimension. So what is motion? Motion is just when an object changes position relative to a reference point. So we've already talked about when an object is changing position. We know that that stems from displacement. If an object changes position, the starting and ending point is different. That is displacement. But now we're talking about, okay, with motion, to prove that something's moving, we have to look at a reference point. Because in this picture, our reference point would, of course, be this tree. It's something that's stationary. With motion, reference point could also be called the origin. We already talked in a previous lesson that the origin is just like the starting point. So maybe this car started at the tree, or maybe there's a rock over here and it started at the rock and that was the origin, and now the car is moving to the left. So frame of reference is very important because it helps prove that you are moving. So whether or not you're moving depends on your point of view. Because if you look at this train car example, we can say that the train car is moving to the left, and this person who has the red dress on says, "I'm standing still." Well, the train's moving, and the red person is saying, "I'm standing still." They're not moving their body inside that train car. But the person in yellow, they're on the ground. They're seeing the person and the train move to the left. It looks like they're moving away. They have motion. So the person in yellow is trying to jump on board. So from inside the boxcar, the woman in red is stationary. If you're looking just inside, maybe the person in yellow gets inside, it does look like they're stationary. They're not moving their legs. But from outside the boxcar, when that person in yellow is on the ground trying to catch up with them, the person in red is moving with the train. All right, here's another example of why frame of reference is important. So frame of reference here, that would include our sun and our tree, and our person is clearly moving past the tree and the sun. So using our frame of reference of the tree, you can say, oh, the person starts to the left of the tree, then they move closer to it, then they run past it. So you're providing evidence that the person is indeed moving. All right, we're going to dig into speed and velocity. And with that, we're going to be talking about average and instantaneous. So first with speed. With speed, to calculate it, you have to know the distance that an object travels in a certain amount of time. So you have to have distance, you have to have time in order to calculate it. So the equation for average speed that you definitely need in your notes is that it's the total distance divided by the total time. So let's say a person moves to the left, to the right, to the left, to the right. You would add each distance, add all of them up, and for each segment that they moved, you add up all the time, and then you divide them. That's how you find the average speed. Now, instantaneous speed, instantaneous has the root word instant, so it's the speed of an object at an instant in time, at a specific point in time. All right, so with average speed, again, maybe the total distance that you travel is the 45 kilometers, and you travel this in apparently 3 hours. So your average speed would be your total distance, the 45 kilometers, divided by your total time. It took you 3 hours. So 45 divided by 3 is our 15 kilometers per hour. So this again would be our average. So our average is 15, but if you look at this speedometer over here, this reading, we can see that the instantaneous speed is 22 kilometers per hour. So at some instance in this journey, your car, your body, however, whatever you were moving in, went 22 kilometers per hour. But overall, the average was 15 kilometers per hour. So they don't always have to be the same, but sometimes they could be. All right, speed. Let's talk about speed. So speed, I know everyone thinks like, oh, you're going really fast to have the speed. Well, think about a turtle. So speed could be how fast or how slow an object is moving. Speed is a scalar quantity. We've already talked about scalar quantities and how they focus primarily on the magnitude, so the number value. Speed is always positive because it relies on distance, and we already know that distance is always positive. Speed never includes direction. So anytime you're telling me a speed answer, it will never include direction. All right, the formula for speed. We already know, and I see that my formatting is a little bit off here, but we already know that it's distance divided by time. I don't really write it with this division sign like this a lot. Normally, it's written like speed equals distance over time. This is how I write anytime I'm going to divide something. So you'll see a lot of triangles in this class. So distance will go on top. Notice how in this format it already kind of looks like a triangle. So speed and time are on bottom, distance is on top, and this triangle just helps us if you have to solve for distance or time or something other than speed. So you cover up whatever you're solving for. Let's say for this first example, you're going to be solving for time. We have distance on top, speed on bottom. So that tells us that we're going to divide distance divided by speed. Let's say we're solving for speed. We know that speed is distance divided by time, and in our triangle, yes, distance is on top, time is on bottom. And then lastly, if you're solving for distance, how far something went. Notice how time and speed are beside each other. That means you're going to be multiplying. So distance is time times speed. All right, changing gears for velocity. So velocity is similar, but not quite the same as speed. Velocity is the object's speed and direction. So it's super important that now with velocity, you are including that direction. So let's say we have a sailboat and the direction changes. We're going north, maybe we're going northeast, then all of a sudden we're going east. The wind is really changing our direction here. So because the direction is changing, let's say the sailboat goes a constant 20 miles per hour. But if the direction is changing, the velocity is also changing, even if that speed is staying the same. So sailboats have a changing velocity. It's constantly changing. Unless they're going in a perfect straight line, same direction, it's changing, even though the speed is staying the same. All right, so again, because velocity depends on direction, as well as the speed, how fast or how slow you're going, the velocity of an object can change even if that speed remains constant. So another example that you might see is a race car. Let's say that this race car is going 55 miles per hour, and it's going all the way around the track. Maybe it's in cruise control, but we're changing direction. So even though the speed is constant, the speed is still 55 miles per hour, the direction is changing. And because the direction is changing, the velocity is changing. All right, so here's our notes for velocity. Velocity is a vector, and we already know from a vector that it includes direction. So you should have a positive or a negative, or a left or a right, or a northeast, southwest, some sort of direction included with your answer. So again, speed and direction. Speed, how fast or how slow? Is it 20 miles per hour? Is it 15 miles per hour? And direction, left, right, forward, backwards. Instantaneous velocity is similar to instantaneous speed. It is that speed and direction, because we're talking about velocity now, so anytime we're talking about velocity, again, direction, at an instant in time, because we're talking about instantaneous velocity. All right, the equation for velocity. You can write this in several different ways. So some physicists use vector arrows on top. And these arrows just remind you that, hey, there's a direction that should be included. A lot of times I write it like this. Velocity is equal to the displacement divided by the time interval, or the total amount of time. So velocity is a unit of length over time. Because distance we know is in meters, time is in seconds, our units for velocity will be meters per second. And that is the same for speed, because speed was distance divided by time, still meters divided by seconds. All right, so if you like the triangles, here's one for velocity. So with velocity, it's the same format. We're going to have velocity on bottom, time on bottom, but on top, now we're going to have displacement. So you can write the entire word if you would like, or technically, I almost ran out of room. Our displacement is represented by an X. Some teachers use an S, but I usually use an X. So with displacement, if you're solving for displacement, which is variable X, you're going to do time times velocity. So if you're solving for the displacement, how far you ended up from the starting point, you're going to take your time and multiply it by the velocity. If you're solving for the time that an object traveled, how long did it take it to get somewhere, you're going to end up doing your displacement divided by your velocity. And if it helps you to write it out, write it out. Displacement divided by velocity. Make sure you understand your notes. All right, so comparing them, speed and velocity. So remember the units. The units for both answers that you will write down will be meters per second. For average speed, when we're talking about average speed, you're telling me the distance traveled, the total distance traveled, where you add up each increment that you have journeyed, divided by the time of travel. So just keep in mind that speed depends on distance. But when we're talking about average velocity, our velocity is dependent on our change in position, or the displacement. Remember, these two are the exact same thing. Displacement is the change in position. So for velocity, you're only looking at, okay, where did you start? Where did you end? Measure that, or calculate that, and then divide it by your time. All right, positive velocity. So positive and negative directions, good news. They're going to be consistent with displacement. So if we're talking about positive, we're talking about, okay, we've moved to the right, we've moved up, north, east, some sort of positive direction, and that the object is changing position. If we're talking about having a negative velocity, that means that the object's moving some sort of negative direction, left, down, south, west. But again, the object is changing position. The last type of velocity that you could have is a zero velocity. Zero velocity doesn't always mean that the object's just stopped or at rest. So it could mean that there's no change in position, or it could mean that the object is actually moving but not being displaced. So you could walk in a big square and end where you started. Walk in a big circle, end where you started. So anytime that you don't have a displacement, you've started and ended exactly where you've began, that will give you a zero velocity. So you could be moving, but if you end where you started, zero velocity. All right, last exercise. So which would be faster? Faster as in, think about, this is what you want to program your car to be. Which one will move faster? So positive 20 or positive 40. And there are 4 examples. I want you to pause the video, go ahead and think about it, and then press play when you're ready for the answers. All right, the answers for each one include 40, because remember, positive and negative, that just tells you direction. Positive, you're moving to the right, negative, you're moving to the left. But if you want to win the race, you obviously want to be going 40 meters per second, not 20, because 40 is going to be faster. So this one, we're just moving to the right, we're moving to the left, we're moving to the left, we're moving to the right. But in every scenario, 40 meters per second is going to be faster than 20. All right, so in review, how are speed and velocity similar? Well, they both measure how fast or how slow something's going. How are they different? Well, velocity includes direction, but speed does not. So velocity tells us that a car is moving 5 miles per hour east because it includes direction. So is velocity more like distance or displacement? Well, it's more like displacement because it includes that direction. So remember, velocity and displacement include direction.